Then after Tycho Muller has been worked on by other mathematicians, and now we are all reading the mathematics books and finding enormous gaps. For example, the fourth loop in the Tycho Muller space is not yet tabulated. So we have to learn mathematics. At the moment we have to invent the mathematics, the physicists have to invent it, or the mathematicians have to do it for them. And so it will take us a fairly long, for example, this young man Witten, who is the most bright man at the moment in this subject, he's about 31 or so. He says, this subject will occupy us for the next 50 years. That's his prediction. Now we should listen very carefully to him, because he is the most profound man at the moment who writes on this subject. And so, and many Indians, that's what I was saying.
I see.
That's what I was saying. These Indian young men, both here as well as in the US, are fully in the thing, at the highest reaches of the subject. So you should be very glad about that.
But what is there something new epistemologically which one is learning?
Well, epistemologically it's all upset everything you knew about theories. For example, as I said, Einstein's theory was based on curved space-time.
Yes.
You remember, Einstein said there's no gravitational force as such, it's all curvature of space and time. Why is the curvature coming out of string theories? Why? We don't know. See, it's the funny thing, as I said to you, you start the theory in 10 flat space-time dimensions, and out comes a curvature. It's a funny thing.
It is understood well enough. It's not mysterious.
It's not mysterious in the sense that we do it every day. But it's mysterious in the sense that we do not know why it's happening. So in that sense, all symmetries are in the thing, but we don't know why. We don't know why. We could not have predicted unless we had solved the equations. And this is a new situation for us, very unpleasant situation. So we have to change that, we have to do higher order calculations, we have to see that the thing works properly and so on. And so it's a fascinating stage. Any young man worth the salt, he should be, if he is minded that way, and he is good in mathematics and so on, he should be encouraged to keep at it for the next 10 years or so. And if it doesn't make any good, then he should go away.
It is not merely just an elegant description of
not at all. We don't understand it.
Or elegant economic description of, but it is deeper than that.
Something totally new, which happens to give at the end of the day the same things we've been doing before. But why? We don't know. It's a very, very strange. Of course, it contains much more stuff besides what we know. Many more things. But those we don't care about. We at the moment are worrying about the zero frequency things like the graviton and like the gluon or like the W and the Z and so on, the normal W and Z of the photon. They all come out of the damn thing.
The masses and properties.
No, not yet the masses. But the properties come out. We know how to get, we shouldn't say we know, but we have the possibility perhaps one day of getting the masses and so on. This is a long, long way off yet to get everything out. But the hope is that everything will come out. And so far the one loop calculations have proved to be finite. And that's the funny thing. So it's a really a totally new world which has opened up for the theorists. For the experimentalists, they couldn't care less. No, they're right not to care about it, because if we keep changing our predictions, they can't take any serious notice.
But you know, experimentalists, poor experimentalists, what they get to do depends so much on the prestige of what a theorist is saying. Otherwise they don't get funded these days.
No, that's a great pity. But you see, they don't get funded anyway now. I mean, take the old theories, which we are sure about, the theories of supersymmetry, so-called, and so on, for which we need an SSC, so-called, a big big accelerator of 20 TeV plus 22 eV.
Supersynchrotron or something.
Yes. Now that is not being funded in the US, for example. And so it's a very, very serious situation at the moment.
What can one do in terms of astronomy to do experiments which would be of specific importance to particle physics?
Well, one of the 3 or 4 neutrinos, for example, from the helium abundance in the universe.
Helium being about a quarter of hydrogen.
Helium being a quarter of the universe.
And supposed to have been made all in the early universe.
That's right, very early universe. Now, the number of neutrinos depends upon that.
Yeah.
This was 3 or 4. Now, experiments found, first time the experiments in the laboratory confirmed something from cosmology, that the number of neutrinos is most likely to be 5.4 plus minus 1.
Sorry? 5.4 plus minus 1?
Yes.
Oh, this is just from the closer, from the acceleration parameter and so on.
That's right.
Otherwise, the total amount of...
No. This is the laboratory experiments on the width of the Z0.
I see.
Which is connected to the neutrino.
All right. Okay.
Now, the 5.4 is, well, it's near 6 or 4 or something. This is a larger number than 3, for example. Now, they re-examined, this is John Ellis and others, they re-examined the data on helium-4 and helium-3, and they find that in fact, according to the new data, up to 6 neutrinos are allowed.
I see.
So that's one thing which will now form a more detailed measurement of the helium abundance, more accurate helium-4 and helium-3 abundance will be called for.
Yeah.
Which the astronomers could do.
Well, the trouble is where you look, it varies a bit and so on and so forth.
Well, this is one point. The other point I was mentioning again at Bangalore yesterday was the existence of Cygnus X3.
Yes.
This object is giving out the pulses of X-rays, and probably...
High energy gamma rays also.
That's high energy gamma rays also. And it's producing muons at the end in the atmosphere. 4.8 hours cycle. It's got the luminosity of 100,000 suns. So it's an incredible accelerator, if you like.
Yeah.
And 10 to the 5 TeV, 10 to the 5... It's an
1,000 GeV.
1,000 GeV. It's an incredible energy with which it's pouring out lots of material. Now, if there could be other such signals, they could be extremely valuable. Extremely valuable. So if you really wish to look for astrophysical things...
What about things like neutrino mass?
That's another example of... that will provide another very important input among the parameters which will be very useful for eventual theories. Another place to look for where astronomy can provide stuff is invisible mass.
Yes.
One believes, as you know, that the mass is probably 1/10. The mass now seen is probably 1/10 of what it is.
Some people say that maybe it's in neutrinos.
Maybe it's neutrinos, maybe it's gravitinos, maybe it's photinos, maybe it's all sorts of speculations are made. The precise nature of missing mass, if there is some, would be extraordinarily welcome for our theories. So astronomy can do a lot for particle physics. Another thing on which astronomy could cast a lot of light is the variation in the fine structure constant with time and the variation in the gravitational constant with time.
I know, but what accuracy do you need?
Well, already we know that it's not varying to 10 to the minus 13, 1 part in 10 to the minus 13. We need better accuracies than that. We need something like 10 to the minus 17 or 16 or something.
1 part in 10 to the minus 13.
For G dot or G, for gravitational constant or G dot or G.
You know it from astronomical evidence, right? Astronomical and archaeological,
and also
geological
arguments, yes.
Yeah.
Yes. So if you could do better on that, that would be another good parameter.
I don't know how astronomy would do much better than that. Maybe. Measure up to redshifts, what, 5, 10? It's difficult. Redshifts 3, 4, 5, one is gone. But
Yes. But anyhow, these are various things on which astrophysics and astronomy, early cosmology could help us. But the thing, as I said, was the fascinating vitality of the subject. Incredible.
I think the magnificent part is one is here talking of range of times 10 to the minus 43 to 10 to the 30 years.
10 to the 43 seconds.
Minus seconds to 10 to the 30
17
years.
seconds.
Yes.